In a previous video, we looked in detail at the predictions of the ideal gas model. Now we want to go look at the real-world situations that we'll be using when we solve problems. For a gas like helium, the ideal monatomic gas model works extremely well. In this case, a single atom gas has 3 degrees of freedom related to its motion in the x, y, or z directions. And equipartition requires that the energy associated with each of those 3 degrees of freedom gets 1/2 kT. Therefore, each atom has 3/2 kT. N atoms has n times 3/2 kT. If we rewrite this in terms of moles, the internal energy is just 3/2 nRT. Based on this result, the heat Q at constant volume will just be the change in internal energy, 3/2 nR delta T. Now what we do is we define the parameter for the heat Q at constant volume be NCV delta T, where CV is the specific heat per mole at constant volume. That is, it's the change in internal energy with respect to temperature per mole. And as you can see from what I've written down here, that's going to be 3/2 R. So the 3 degrees of freedom gives us a specific heat at constant volume of 3/2 R. The specific heat per mole at constant pressure is just CV plus R. This is a result that we will derive when we get to looking at what work says about heat and the first law of thermodynamics. But for now, I'll just note that this means that CP is 5/2 R. These two results agree with experiment, as I've already shown you. If we look at a graph of neon, as long as we're above its boiling point, it has a slope per mole of 3/2 R. In fact, as long as we are away from what happens as it condenses into a liquid and eventually becomes a solid, say at temperatures above 50 Kelvin, everything is very well behaved and in good agreement with this ideal model. Experimental data for other ideal gases, that is, noble gases, is similar. So as long as we're well away from the phase transition, as long as they're a gas, say at room temperature, this result of CV equals 3/2 R can be used for thermodynamic problems, and that's what we do. We also looked at a diatomic gas. This is a little bit messier. That the result does depend on temperature in a way that's not simple at all. A single molecule at, say, room temperature has 5 degrees of freedom, 3 for translation plus 2 for rotation. We'll see what this means when we look at some results from experimental data. Equipartition requires that the energy associated with each of the 5 degrees of freedom gets 1/2 kT. So each molecule gets 5/2 kT. N molecules gets N times 5/2 kT. And if we write this in terms of moles, we'll get 5/2 nRT. If we look at this result and look at the heat at constant volume, again, the change in internal energy is 5/2 nR delta T, and we see that the change per mole is going to be 5/2 R. So if we rewrite Q in terms of NCV delta T, we see that CV, the rate of change of internal energy with respect to temperature per mole, is 5/2 R. That's the specific heat per mole at constant volume. At constant pressure, it will be larger by R. So CP is 7/2 R if we want to use the specific heat per mole at constant pressure for a diatomic gas. These also generally agree with the experiment, but only within a certain range of temperature. Here's a graph of data for hydrogen gas as a function of temperature on a logarithmic scale, except that the number of moles have been divided out and the derivative has been evaluated. So what's being graphed here is actually the derivative of the internal energy per mole, that is that slope we've looked at before, the specific heat at constant volume. You notice in a temperature range from roughly 0 degrees Celsius to roughly 450 degrees Celsius, the horizontal constant line of 5/2 R is in pretty good agreement with the experimental data, which has been summarized with that red curve that you see in the graph. It doesn't work quite as well as one might like around 0 degrees Celsius or at the higher temperatures, but in that intermediate region, which happens to be the kind of temperatures one encounters inside of an automobile engine, some other things that we care about in the real world of engineering, 5/2 R works pretty good. And the experimental data for air, meaning nitrogen and oxygen, are quite similar to this. And because of that good agreement, many thermodynamic problems involving air are analyzed using CV equals 5/2 R and CP equals 7/2 R, even though they're not in perfect agreement with the data. They work extremely well at certain temperatures where the agreement is actually in the third sig fig. Solids aren't quite as simple. There's a model for solids, but we always use data because the model does not give 3 to 4 sig fig agreement like we get for gases. In fact, iron happens to be one case where it works pretty well. The model is called the Dulong-Petit law. It says that the specific heat per mole should be about CV equals 3R for every solid. That value of 3R for this constant volume specific heat is also the prediction for a triatomic or polyatomic molecule, molecules that lack the simple symmetry of a diatomic molecule. However, this prediction works, although it works well for iron, doesn't work so well for other elements. For iron, it says the specific heat per kilogram Kelvin should be about 0.447 kilojoules per kilogram Kelvin. So specific heat per mass is actually in excellent agreement with the kind of number that we would use to do calculations. However, for lead, when we look at the specific heat per unit mass, it's off by about 6% or so. Not as good agreement as we would like with the value of 0.128 kilojoules per kilogram Kelvin that we use for problems. For aluminum, now the prediction is a little bit high by maybe 3% or so, where we would use maybe 0.9 kilojoules per kilogram Kelvin. However, when you get to one of the worst case examples, beryllium, the prediction is 2.8, but experiment says 1.8. This huge error is an example of why we simply can't rely on using a model like the Dulong-Petit model for any real materials. We just use experimental values. Nonetheless, it does give us an idea of why we can get away with using those experimental values. The behavior of that solid is pretty linear. Its internal energy increases gradually with temperature, with a slope that we can maybe estimate from a model. And as the temperature increases, the vibrational energy of those atoms at a particular spot in that solid increases at a rate that one can basically understand until it reaches the melting point. At that point, things change dramatically. The internal energy increases by increasing the potential energy rather than the kinetic energy. That is, the average kinetic energy no longer changes. The temperature is constant during that phase transition. Now, to look at this in more detail, we're going to go to water, which is something that we use for many different things in regular daily life, and so it's a better example for this particular situation. There's actually nothing simple about water in any of its forms. It's solid form that we call ice, it's liquid form that we call water, and it's gas form that we call steam. I'm going to look at this as with a graphical presentation. We're going to use measured values for the specific heat, that is what happens when temperature changes, and the latent heat, what happens when the phase changes. And I've organized this in a graph that's different from the ones you typically see in textbooks, where again I've plotted the energy on the vertical axis and temperature on the horizontal axis. Doing this, then the slope of that graph is in fact the specific heat. In its solid phase, water, meaning ice, behaves like other solids. It has a fairly linear behavior up until it reaches the melting point. A specific heat value for ice that we'll use when ice is in its solid form. That's a valid temperature-dependent result that's valid just below freezing. Now you'll notice that there's something happens after that, but I don't want to talk about that at this moment. The important result here is that in the solid phase, there's a steady increase in internal energy with temperature, reflecting the fact that the average kinetic energy is directly proportional to the temperature. That is, something gets hot when the average kinetic energy has increased. But now there's a jump where the temperature does not change. Internal energy has increased without a change in temperature because that energy has gone into breaking bonds, that has gone into changing the potential energy of those molecules in that solid as they become molecules in a liquid. There's there's energy required to break the bonds that have held those things in that rigid solid form, and that energy we call latent heat, symbol L. The discontinuous jump from solid to liquid phase is a first-order phase transition. The temperature is constant. The average kinetic energy does not change. The atoms aren't moving any faster when they're in the liquid. What the heat energy has done is changed the average potential energy by breaking bonds rather than making the atoms go faster. Now that it's in a liquid phase, again, the energy increases in a nice linear fashion. Although it's not exactly linear, the value for the specific heat that we'll use, 4.184 kilojoules per kilogram degrees Celsius, is really only valid at a particular temperature. It varies in a slight fashion as we go across there because, as I said, water is not a simple material. Nonetheless, we'll just treat it as a nice linear behavior from the point where it became a liquid to the point where it becomes a transition into a gas. That vertical jump there, that very large vertical jump, is associated with the huge amount of energy required to break the bonds, as it were, that hold the molecules in its liquid state, allowing them to move freely as a gas. That large energy, that large latent heat, is why evaporating water cools us so well and why condensing steam can burn us so badly. There's a huge amount of energy associated just with making that phase transition. The term latent heat conveys the idea that this is hidden energy that cannot be detected by measuring the temperature of the object. It's energy that can be released when the bonds form to put the gas atoms back into a liquid state, or that has to be removed from you in order to make the transition from liquid to gas. Once it's in its gas phase, it again has a nice linear slope, although at a different slope than it has as either a liquid or a solid. And although now I must comment that in this case, this is now at constant pressure. In the solid and liquid states, the change in volume with temperature isn't really a big deal, especially for water. But once you go into a gas phase, there's a change in volume. So this is the constant pressure result, and part of those energies that you see graphed here are due to the work done for that change in volume that has to take place at constant pressure. The data that we use are always constant pressure values because those are the situations under which we tend to work with ice, water, or steam in problems that we encounter in this course. In engineering applications, you'll use what are called steam tables to look at the values that you would use under other circumstances. I'll just leave it there. So one of the results in here is taken from the OpenStax textbook. I don't know if I mentioned that at the time, but I give the reference to it here.